I am Michael Battaglio. I am Juan Laura's postdoc. I'm really excited to be talking to you today. I come from Mars. I did all of my PhD and first postdoc work looking at Mars stuff, and I'm really excited to be talking about some new research that we're going to have out in Nature Astronomy. They've given it a DOI, so they can't take it away now. It's too late. So hopefully in a couple of weeks, you will see that. So I want to talk to you about annular modes of climate variability on Titan. And I'm sure a lot of you are wondering what the heck is an annular mode. So we'll break it down in pieces. First of all, a mode of climate variability. There is an example you're probably all familiar with already, which is just El Nino, La Nina. That's a mode of climate variability. And all that is changes in trade winds in the Pacific mean changes in sea surface temperature and precipitation across the whole globe. So changes of a specific quantity in one place have global impacts, or they can. So what makes a mode annular or not annular? Well, INSO is not annular. So to make something that is annular, all you need if you're looking down at the pole is that the shape of changes in the mode is in a circle around the pole. So the fancy way of saying that is changes along all longitudes at a given latitude circle are correlated. That's the fancy way of saying it. Something you might be sort of familiar with is the intertropical convergence zone. That's sort of annular. Now, what this looks like in practice, I've shown us a couple of examples here. First of all, here's the eddy kinetic energy. This is a beautifully shaped annular mode. It's a circle around the southern pole. Something you might care more about, though, is that the precipitation on Earth is associated with this mode in eddy kinetic energy, and it's also annular. It doesn't have to be a circle around the pole, though. It can be just a blob right at the pole, because it can still be annular if it's 89.99 degrees of latitude. That's still annular. Here's an example from Mars. And we can make use of this symmetry and simply fold everything along a given latitude circle together, take the zonal mean, and really simplify the analyses for this particular process. I've shown this down in the bottom right panel. This is just a blob that's just like from the eddy kinetic energy up in the top left panel, and it's just averaged together. So it just looks like a blob in latitude pressure space. The whole reason that set me off down this path is I noticed in my last postdoc with Helen Wang, developing this Mars dust activity database from images from Mars, that dust storms, which are just these peaks in the curve in this figure here, you don't need to know any more detail than just that the dust storms are spread out evenly in time. They have a specific periodicity associated with them, which reminded me of one of the annular modes on Earth, which also has this periodicity that comes and goes with time. So I went searching for these on Mars. Lo and behold, they were there. And then Juan suggested, well, let's just look at Titan too. And big surprise, they're there as well. So before I show you these pictures, the way we are searching for them is we're going to take Juan's model, the Titan atmospheric model, which we'll talk about in the next session, and then two reanalysis data sets for Earth and Mars. Take the zonal mean of these data sets. We have these nice long time series, and then do an empirical orthogonal function analysis on them, which is just a fancy linear algebra way of saying to decompose things down into their eigenvalues and eigenvectors. And for comparison purposes, I kind of color coordinated things so you don't get confused, and hopefully I also don't get confused as well. I've color coordinated Titan is yellow for its hazes, Mars is red for its dust, Earth is blue for its oceans. So hopefully I can remember them at least. And what you're looking at here, so this shading shows you what the most important source of variability in the fields that are contoured are. So this first mode, Earth has two of them, is in the zonal mean zonal wind, which is contoured. And for Earth and Mars, down at the bottom, these dipoles, these red and blue shadings, shows you that the most important way of variability of the zonal mean zonal wind is that it just shifts back and forth, north and south. Titan is quite different though, because its jets are formed very differently from Earth. So instead of the zonal mean jet just being this blob in the center, you have superrotation, and then these extensions of the jet down and towards the poles. And so they don't shift north and south, they actually shift up and down. Another thing that makes Titan weird, and it's basically going to be the theme of the rest of this talk, is Titan is weird, newsflash to everybody in the audience, is that for Earth, we say that this mode is barotropic, as in it's stacked vertically. You can kind of see it. I've just copied the shading from the previous slide onto contours on this one. It's stacked vertically. Titan is anti-barotropic, if there is such a thing. It's stacked horizontally, if you can have something stacked horizontally. For Earth and Mars, though, you get this bullseye of eddy momentum fluxes, which just is a suggestion of how much energy is being transferred from the eddies to the mean flow, and the convergence and divergence of these fluxes line up with the two poles of the mode. You don't get that at all for Titan, though. The placement is totally wrong. So Titan is weird. The second mode is in the eddy kinetic energy, which is just a quantification of the amplitude of the mode. For Earth and Mars, it's just this blob around the mid-latitudes, kind of midway up in the troposphere. Titan has a similar story, though, even though its averaged eddy kinetic energy in contours doesn't line up with Earth and Mars. It looks somewhat different as well. So we call this barotropic annular mode. One thing I forgot to point out about the barotropic one is that even though Titan is very different, so I've just jumped back a slide, sorry. It's that the percentages of variance explained, these are the eigenvalues associated with the eigenvector maps. The variance explained is much higher for Titan than it is for Earth and Mars. So these modes are much more important for explaining variability. And the same story is true for the eddy kinetic energy mode as well. We say that this eddy kinetic energy mode is a baroclinic mode because the shapes of the modes are tilted for Earth and Mars, and it's associated with eddy heat fluxes. These eddy heat fluxes are what drive these eddies that are part of the mode in the first place. So it makes sense for Earth and Mars that they're correlated. For Titan, though, the story is both upside down and backwards somehow. Because while you get positive heat fluxes in the northern hemisphere for both Earth and Mars, you get negative heat fluxes in the main core of this mode for Titan. And you get this dipole of heat fluxes as well. So the waves that are generating this eddy kinetic energy are not baroclinic. The baroclinic waves, which Juan will talk about later, are actually the ones that I showed you in the previous slide. That's this eddy kinetic energy right here, but it turns out to not be variable. The thing about this mode is while the barotropic mode, that mode in the zonal mean zonal wind, shifted back and forth, remember, this bullseye of the mode just means that the eddies pulse with time. They just come and go, just like those dust storms that I showed at the beginning, which set us off on this whole path in the first place. So now, having gone through all of that dry dynamics, why should anyone else in this audience care except me and Juan? I said at the onset that these modes of variability can control sea surface temperatures and precipitation and temperatures throughout Earth. And this is just the repeat of that precipitation figure from earlier in the talk. This is just the mode regressed back onto the precipitation. And the precipitation stands out really well. For Mars, a similar story happens because the same kind of waves that make large precipitation in the mid-latitudes on Earth are the same type of waves that make big dust storms on Mars. And here is Mars's eddy kinetic energy annular mode regressed back onto the dust. And so these dust events start in the northern hemisphere and they flush to the south. That's what this negative and positive regions indicate. For Titan, though, the story is again weird in that here's the principal component, which is just the time series associated with that dipole moving up and down of the winds. And the peaks turn out to line up with big precipitation events. Not only that, the same peaks that happen in the eddy kinetic energy mode line up with the peaks of the barotropic mode. So the U and the eddy kinetic energy line up. This does not happen for Earth and Mars. We speculate that the reason that this happens is because each of these peaks here are the peaks of precipitation events in TAM as well. And so while we may not be able to causally link which comes first, the mode or the precip, they are related. And so if we explain one, we're going to explain the other. So we should all care about this. And so it's going to take a lot more effort. Stay tuned for Titan through time 6. Lest you all walk away and say, Titan is completely ridiculous and weird, and it's so awesome to study Titan, I'll end with this just by showing you it's different in many ways, but when we fold everything back out from the zonal mean and look at the annular structures again, boy, do they look remarkably similar. You get this peak right around the mid-latitudes, and each of these peaks for Earth and Mars are the storm tracks for the precipitation and dust, respectively. And we're really excited to be hopefully getting topography into TAM soon, and we're going to be rerunning these analyses. Look for a lot more papers from me and Juan in the future, hopefully. And with that, I will take your questions. Thank you so much.
Okay, thank you very much. We do have time for some questions, so fire away.
You use like different models, like the last slide you just showed, right? So how comparable are those models actually for like Earth, Mars? It seems like it's all different models, right?
So for Earth and Mars, I didn't talk about it very much. It's a good question. So they're reanalyses. So for Earth and Mars, we have the benefit of having stuff going around the bodies at all times. And so the reanalyses are models, but they're constrained by observations. So the models just don't go off and do their own thing. It's actually representing, it's our best representation of what the atmospheres of both Earth and Mars are doing. So those are fairly well constrained. They have their issues, especially Martian reanalyses, because there's just not nearly as much data for Mars, obviously, there is for Earth. You know, there are dozens and dozens of satellites around Earth, but only like 2 for Mars, and then, you know, 0 for Titan. So, so you know, we need more data. That's the theme of every single one of these conferences ever. I think we need more data.
You're looking forward to adding the topography results, actually.
I'm sorry?
And looking forward to after you add the topography. Yeah.
Yeah, thank you.
Paul Hain, University of Colorado. Yeah, really, really interesting, and I can't wait to see the paper. Would this have, you know, would the vertical shifts in the jet have any impact on the polar atmospheric chemistry, or something that we could actually detect either with existing data or maybe some of the ground-based observations like with ALMA and stuff that's ongoing?
I'm going to answer first by saying yes and maybe no. The winds, so I didn't show it, but the modes themselves also regress back on to temperature as well, not just the winds. And so when these modes, the shifting up and down is also associated with a temperature change as well. So the answer is maybe, specifically what they are. Maybe a good thing for Juan. He's already raising his hand. Go ahead, Juan.
Well, let's quickly take a question online from Rick.
Just really quickly, just to follow up on that. These modes are in the troposphere. And so I think thinking about stratospheric chemistry is a different story. But maybe it connects because the winds are, you know, the zonal winds are connected between the troposphere and the stratosphere.
Rick?
Yeah, nice talk, Michael. I was just actually going to ask about what Juan was just mentioning, is where are you looking at those modes for Titan? And the mid-latitude jets on Earth are primarily driven by waves or eddies and baroclinically driven instabilities. So are you suggesting that maybe what we're observing on Titan is a similar effect?
So you have opened up a whole can of worms or beans or whatever the cliche is, because there is a big argument right now in the annular mode community for Earth on how the modes are related, because there should be a strong relationship between the eddy kinetic energy mode, the baroclinic mode, and the barotropic mode for exactly the reason that you said, which is that the eddy-driven jet is, well, driven by eddies. However, the story is also complicated by the fact that the eddy-driven jet is not always a distinct entity on Earth anyway. A lot of it is subtropically forced, especially in the zonal mean. You only get the separate structures when you look at specific groups of longitudes. So to answer your actual question, which is, are we suggesting that maybe the jets are forced baroclinically on Titan as well? The answer is the baroclinic part of the waves is much closer to the surface than this particular mode. So we definitely are not confident in saying that the jet is baroclinically forced. It's an annular momentum conserving sort of process primarily. The baroclinic waves are only important very, very near the surface. I think I answered your question kind of long-winded.
Yeah, yeah. No, thank you so much. Yeah, that's an interesting take. Thanks.